All right, so the recording is live. Hey everyone, welcome to this week's lecture. I'm going to be trying to basically write today's lecture, so kind of more like Ethan does it. So we'll see how that goes. Yeah, I guess let's get started. So we ended off last week, at least I ended off last week, talking about this notion that we have of signed volume. And these are going to be some big notes, so I'm going to have to use lots of note pages, right? And so signed volume is basically this function that we run on a matrix. So it takes in a matrix A, and what it does is it takes in a matrix A and it computes the volume of the shape made by its columns, plus or minus, so times a sign. If you want to go over exactly what it is, you can look back at the lecture notes from last week. But we start with the assumption. Ooh, that's wiggly. That signed volume, which I'm going to from now on denote as SV, because I am now writing with my finger. SV of the identity matrix is always going to be 1. And if we start with the matrix A that has columns A1 through AN, and we switch any two of the columns. So let's say we have, let's call this B. This is going to be, let's say, A1 ... AI. Oh, I'm using the wrong notation. A1 AI. That's going to be AJ. AI. AN. So basically, all I've done here is I've just this is a bad J, but I've swapped two of the columns. Then in this case, we say that the signed volume of A is equal to the negative signed volume of B. And again, it turns out from these two properties, you can uniquely determine everything you want, basically, about this function, signed volume. So that's a little bit of review from last week. Are there any questions about that? Actually, I'll leave it up. Okay, so moving on, I told you last week that the whole reason we were doing this signed volume thing is because it turns out that the determinant is just signed volume, which I think is kind of interesting. It's something that people don't necessarily explain, and it is actually kind of, in some sense, the better way of thinking about the determinant is as signed volume. There's a really beautiful and rich sense in which, again, like the signed volume uniquely defines the determinant. However, when the rubber meets the road, we need a way of computing signed volume. And I am going to present that formula to you now. And I will apologize for this formula in advance. This formula is terrible. So we'll start with its nicer counterpart, which is the determinant of a 2x2 matrix. Now, I'm going to use the notation det of A to mean the determinant of A. And remember, all this is really is just signed volume. Right? So this is really the same as SV of A, but we want to compute it. Now, another way of writing the determinant is like this. Right? And that can be a little bit confusing. Oh, is something, okay, yeah. That can be a little bit confusing because normally we think of the absolute value of being positive, right? So, if I have absolute value of x for x, or I guess let's go absolute value of alpha, absolute value of alpha is always greater than or equal to 0. But the signed volume is, not necessarily greater than or equal to 0. So it's a little bit funky, but one way to think about it is the absolute value of x is really just kind of asking what the size of x is. And so the determinant of a matrix is also asking what size it is. So that's one way of thinking about it. I will basically never use this notation. However, when I am explicitly writing the matrix out, I might. And what I mean by that is this here with the straight sides, this is the determinant of the matrix A, B, C, D. Okay? So like, I'll use the straight sides when writing out the matrix, but I'll never put the straight sides next to a matrix. And that's because I think it's way more clear in this case that you're not talking about some sort of absolute value than it is in this case. So that's going to be my convention. I won't hold Ethan to this, so he'll have to tell you what his convention is next time, but that's going to be my convention at least. It turns out in the 2x2 case, it's a very simple formula. Actually, let's start with the 1x1 case, which might sound funny, but there is a 1x1 case. We can have 1x1 matrices. And so it turns out, and this is terrible, by the way, this is going to be some terrible notation, that in the 1x1 matrix case, the determinant is just A, which, again, this looks a lot like the absolute value. It's not the absolute value, and so we will never write 1x1 matrices as determinants. So let's go to the 2x2 case. It's just important to note that it is actually just the determinant of a 1x1 matrix is just itself. Now, the determinant of the 2x2 matrix is kind of fun. We're going to do this. Ooh, that's multicolored. We're going to multiply A and D. This is going to be A times D minus B times C. Okay, so for the 2x2 determinant, you just take this upper left times the bottom right minus this upper right times this bottom left. Right? Everyone get that formula? Cool. If you want to, you can work it out and figure out that this is, in fact, the volume, or the area in this case, of the parallelogram made by, this point here is going to be AC, this point here is going to be BD, and this volume is this determinant, times a sign, again. The sign, it's always important to remember the sign. And so that's kind of a very simple formula. So you may be wondering why I'm being so why I'm so worried about the general formula. Well, it's because the 2x2 case is essentially the nicest possible case. Now, there are a lot of different formulas for the determinant, but here is probably the most useful one in practice. And it's going to be a recursive formula, so I'm very sorry about that. But that's just how it's going to be. In order to talk about this formula, we're going to have to define some notation. So if I have a matrix A, okay, I am going to, what is the standard notation for this? Here, we'll do this. I'm going to define this, AI, comma J. This is going to be the matrix that you get by removing the ith row and jth column of A. So for instance, if A was A, B, C, D, E, F, G, H, I, if this is A, then A 2, comma 2, well, this is just going to be we take our original matrix and we're just left with, well, we remove the middle row and column. So we're just left with A, C, G, I. Right? That's not too bad, I would say. There's like 1,000,001 different notations for this matrix, but it's called a principal submatrix, if you want the name. There's a principal submatrix. Principal submatrix. And it's just a matrix you get by removing a row and a column of your matrix. Yeah, exactly. It removes the ith row and then removes the jth column, right? This is not too bad. So here's the formula for, here's one formula for the determinant of a matrix. Okay, so we're going to start, with the determinant of A. And this is going to be so now my matrix A is going to be Aij. I, comma J. Equals 1 to n. So this is an n by n matrix, and the entries of this matrix are going to look like Aij. Okay? So like, if n was 2, this would look like A11, A12, A21, A22. Okay? So in this formula, the determinant of A is going to be A11 times the determinant of A11 plus A12 times the determinant of A12. Sorry, minus. No, sorry. This here is just specifying the bounds. So it's just saying that I and j are going to run from 1 to n. So it's not a matrix power, it's just putting bounds on the matrix, if that makes sense. here's the formula. Isn't that a wonderful formula? Took me a long time to write out. So, things to notice with this formula. The sign changes every time. So the first element in the sum is positive. The second one is negative. The third one is positive. And then the fourth one would be negative. And it just goes down like this until the last one, you just do this -1 to the n minus 1. And that gives you the sign. So if I wanted to write this compactly using sigma notation, which is something that I have tried to avoid the entire time I've been teaching this, this would be the sum from I equals 1 to n of -1 to the n minus 1 a1i det a1i. So that's, for those of you who have seen sigma sum notation, that's how you do it. But the kind of trick of this little symbol here is this is just a for loop. This is just saying you start with sum equals 0, and then you sum from I equals 1 to n of this part here. So this is all secretly a for loop, where you're just adding up something over and over again. So that's the formula. And as you can see, it's recursive. So this here is an n minus 1 by n minus 1 matrix. So if we keep, now we use this formula again, and we use it again, and we use it again, and we use it again, over and over and over again, until we eventually compute the full determinant, which it's, I think, pretty exciting. We now have a formula to compute the determinant. So are there any questions about this formula? I mean, I haven't shown you how to use it or anything useful about it yet, but does the kind of formula make sense? Why does it have to be so complex? Because it does. The thing is, so what I will say is there are much simpler definitions of the determinant that you can use, but they are simple not in terms of they require a lot more prerequisite knowledge than this does. All you have to do here is be able to add things and do recursive functions, which is something that I think most programmers should be able to do. Other methods of computing the determinant are more complicated and also often more difficult to analyze. So that's kind of why it ends up being so tricky. But I want you to notice something. It does. You actually can't, well, the 1-by-1 case you just have to say is true, basically, because there aren't any there are no submatrices of a 1-by-1 matrix. So you have to define some sort of base case. And so the 1-by-1 matrix case you can define as the base case, and then the 2-by-2 matrix case immediately follows from that. But it's actually easier to define the 2-by-2 matrix as the base case. So yeah, it does sound silly. I want you to notice something about this formula, though. In order to compute it, all we ever do is multiply things and add things. Right? We never take any square roots, we never exponentiate, we never take a sine, a cosine. All we do is we multiply and we add. So we could write the determinant not as a linear transformation, but as a polynomial, actually a multivariate polynomial. So for instance, when we wrote out the formula for the determinant of a 2-by-2 matrix, we had A, B, C, D. Well, these are all variables, right? And when we wrote it out, we wrote it as A times D minus B times C, right? So this is a polynomial in 4 variables. You may be asking, why am I mentioning this? Because you've probably never worked with a polynomial in more than maybe 2 variables, probably even only 1, but it does come up. And it will actually come up now. So the next thing I want to talk about is like the whole reason why I even defined the determinant, which is the characteristic polynomial. The characteristic polynomial of a matrix. I'll give it a little exclamation point, though you can't see the exclamation point because it got swamped. Anyway, so we've talked about the determinant, and it has this formula. We're not really going to talk too much more about the formula, but you can now hopefully compute it. So why do I care about the why do I care about the determinant? Well, as we mentioned last time we talked about the determinant, the only case where determinant A equals 0, so the only time when the signed volume is 0 is when A is not invertible. Right? And so I want to dive into that a little bit. Right? Because what this is really saying is, okay, in 2D, the signed volume is going to be like the some number times the volume of this parallelogram, right? Where these points here are the columns of my 2x2 matrix. The only time that area can be 0 is if the columns are actually lying in the same line, right? If they're actually basically, essentially scalar multiples of each other. And in particular, the area can only be 0 if the columns of your matrix are linearly dependent. And this idea translates up into higher dimensions. In 3 dimensions, normally the volume is going to be the volume of some sort of like, oh man, I haven't drawn a parallel pipette in years. It's going to be like the volume of some figure like this, this 3-dimensional shape. And the only way that this volume could be 0 is if actually this 3-dimensional shape was actually just 2D, because one of the vectors is in the plane made by the other two. Right? And so this is exactly what it means for the columns of the matrix to be linearly dependent. So we can't quite get to where I want to be now, but we can say, I hope you believe me when I say, that the determinant of A is 0 if and only if the columns of A are linearly dependent. So linearly dependent columns. Are you willing to believe me on this? From my explanation so far, do you believe that statement is true? Right. So in the 1D case, linear dependence means that the columns must be on the same line. In the 3D case, it means that all 3 of the columns must be in the same plane, right? And in both of those cases, plane or line, both of those cases, the respective notions of volume are going to be 0. It's going to, so what I'm going to work towards is showing you why A having linearly dependent columns means that A isn't invertible. And then once we have that, that also means that determinant equals 0 if and only if A is not invertible. Right? So I'm going to work towards that. Okay. So let's assume now that A has linearly dependent columns, right? And I'm going to call the columns of A, A1, A2 through AN, right? So for these to be linearly dependent, there have to be scalars, and I'm going to name these scalars potentially something weird. Scalars x1 through xn, such that not all of them are 0, right? So at least one xi is not equal to 0. And we must have that x1, a1 plus x2, a2 plus xn, an. This is 0n. This is the 0 vector. Right? That's the definition of linear dependence. Right? So these two statements are equivalent. Okay. So let's let x be the vector x1 through xn. Okay? It turns out from the definition of matrix multiplication, this sum here, these x terms are just the scalars in this linear combination. Right? So linear dependence means that there's a non-trivial linear combination of your vectors that is equal to 0. We're letting, they don't relate to the matrix as much as they relate to the columns of the matrix. Right? So for instance, if the columns of the matrix were 1, 1 and 2, 2, then one choice of x1 and x2 would be to choose x1 to be -2 and x2 to be 1, right? Because then -2 times 1, 1 plus 1 times 2, 2, well, this would be equal to -2, -2 plus 2, 2, which would be equal to 0, 0, right? So in this case, x1 would be this, and x2 would be this. Okay, so right, this is an example, but in general, we're just going to call these things x1 through xn, because we're working in generality here. What did I do? I touched something I shouldn't have. That's what I did. Okay. So we've got this. Okay. It turns out, if you look at this formula up here, the one up there, that's just A times X. And we know from this equal sign here that this must be equal to 0, right? And we also know that X is not 0. So what's this? That's the null space equation, right? So we've just found a non-trivial solution to the null space equation, which means that A having linearly dependent columns is equivalent to A having a null space, or a non-trivial null space, right? So what we've already shown is that the determinant of A being 0 means that A has a null space, which also means that A must have an eigenvalue 0, right? Because as we showed, AX equals 0n is the same thing as saying AX equals 0 times x, and this is the eigenvalue equation for the eigenvalue 0. So right, we've shown that the determinant being 0 is equivalent to A having an eigenvalue of 0. Okay, and we are just one step away, because, well, actually, we've basically gotten everything we need at this point for the eigenvalue discussion, but there's one more step that to get to the invertible, what's called the invertible matrix theorem, or at least part of it, which is to say, okay, let's stop this discussion here for a bit and talk about a matrix inverse. So suppose there's some matrix A inverse such that A inverse times A equals I, right? Suppose that exists. Okay. Then consider the equation AX equals 0, right? This equation is equivalent to multiplying both sides by A inverse. Actually, let's just do a one-sided implication. So this left-hand side here implies that A inverse AX times A inverse 0, these must also be equal, right? Because we're multiplying both sides by the same matrix. So equality is going to remain. Okay. But this is the identity matrix. So this implies identity times x equals, and well, any matrix times 0 is going to be 0. So now we have identity matrix times x equals 0, which implies that x is 0, right? So what I've just shown is that if you're invertible, the only solution to the null space equation is going to be x equals 0. Does everyone kind of get that? Or does anyone have any questions about how what I just did shows that? The kind of way of thinking about it is, all I assumed is that AX equals 0, and just from that assumption, I proved that x is 0, right? Which means that the only solution to that equation must be 0. Because all I assumed is that it was a solution to the equation, and just from that fact, I showed it was 0. And so, if you believe me on that, which if that argument didn't quite land, that's fine. Just if you believe me that a matrix being invertible means that the only solution to the null space equation is x equals 0, well then we have that, well, if we return to our x up here, right, this x here, which I'm going to write it in red now, actually, so that it's to distinguish it from the kind of like variable x we were using in this discussion. So if we have ax, I hit my keyboard. If we have ax equals 0, this must mean that A is not invertible. Okay. And so if we follow back our logic all the way, we go all the way back to the top, what we have now shown is that the determinant of A being equal to 0 is equivalent to A not invertible. Which also means that if the determinant is not 0, then we are invertible. And so that function test that we talked about last week, that function is just testing whether or not the determinant is equal to 0. And that's all you have to do. Okay, and so this whole thing is at least part of something called the invertible matrix theorem, which basically describes all the conditions that are enough to prove that a matrix is invertible. And so it turns out like invertible matrices are incredibly nice. Invertible matrices have linearly independent columns. They also have linearly independent rows. Their determinant is not equal to 0. Every possible linear system that looks like AX equals B is solvable for a unique solution. It's a whole bunch of good stuff. So invertible matrices, 2 thumbs up. We like them. So that's kind of like the invertible matrix theorem. And it's also why like the kind of column space is so important, because once you know the dimension of the column space tells you whether or not the columns of A are linearly independent. And so, right, because if you have an n by n matrix and the dimension of your column space is n, then you must have linearly independent columns. You can kind of run that argument through by yourself if you want, but that basically is saying that if the dimension of your column space is n, then you're invertible, and then everything's solvable. So it's all this kind of really interconnected soup of delicious soup of mathematics. But we're talking about eigenvalues right now. Are there any questions about the invertible matrix theorem before we move on to the eigenvalue computation stuff? Okay. So, if you remember, back to the eigenvalue problem, we can write the eigenvalue problem as AX equals lambda x, right? And the problem we're trying to solve right now is which lambdas have non-trivial solutions. Okay. We can rewrite this problem as we showed last week as A minus lambda I times x equals 0, right? So it's this null space problem again. But remember, we just showed that the determinant can be used to determine, that's why it's called the determinant. The determinant can be used to determine if a matrix, if the null space equation has a solution or a non-trivial solution, right? And in particular, we know that this has a non-trivial solution if and only if the determinant of this matrix here is 0, right? Well, the only unknown variable in this problem is lambda, right? We know A, we have it written down. We know what the identity is, the identity matrix. The only thing that can possibly change to make this 0 or not 0 is lambda. And this, as we mentioned earlier, the determinant gives you a polynomial. So it turns out that this determinant here is going to be a polynomial in one variable. And that variable is going to be lambda. Now you can also show, using the determinant, this is actually going to be a degree n polynomial. So let's do an example really quick. Like before I talk anything more, because I'm going to get too excited, I want to do a really quick example. I want to prove to you that the identity matrix has 2 eigenvalues that are both equal to 1. Okay. So what we're going to do is we're going to form the eigenvalue matrix we're going to do the I2. So we're going to do I2 minus lambda I2. Well, this is just 1 minus lambda, 0, 0, 1 minus lambda. Now, something you're going to show in your homework is that the determinant of this matrix is just 1 minus lambda squared. Turns out if you have a diagonal matrix, the determinant is just the product of the diagonal. Okay, what are the roots of this matrix, of this polynomial? Well, it has one root at 1, right? But that root has multiplicity 2. Right? So if you remember from algebra class, I hope you learned that polynomials can have roots of higher multiplicity. So right, if this is 1, and this is 1, right? What this is going to look like is it's going to look like a parabola. It's going to come into at 0. It's going to reach 0 at 1. Sorry, I crossed a little bit. It's going to be equal to 0 only at 1, and then everywhere else is going to be positive. And we say that this root here, this root, that's not there. This root at 1 has multiplicity 2. Right? Because, it's basically at lambda equals 1, this is going to be like 0 squared. Right? And so we count this twice. And so it works out that the two eigenvalues of I2, that's not I2. The two eigenvalues of I2 are going to be 1 and 1. Right? And so in general, a polynomial of degree n will always have n roots. And those roots are going to be the eigenvalues of your matrix. So to find the eigenvalues of your matrix, all you do is you take the determinant of this matrix here. That gives you a polynomial. Then you find the roots of that polynomial using algebra or whatever method you want, and those are the eigenvalues. And this is also why I can say that if you count the eigenvalues correctly, every matrix has every n by n matrix has exactly n eigenvalues. Now I want to point out something real quick. As you may know, sometimes polynomials have imaginary roots. And it turns out this can happen with matrices too. You can have a matrix where you take the determinant of that equation, and everything's real numbers, right? But you might end up with this polynomial. Maybe the polynomial ends up looking like lambda squared plus 1, right? Well, it turns out the roots of the solutions to this problem are lambda equals I, where I is the imaginary number square root of 1, and negative I. Now, if you haven't seen imaginary numbers, fair enough. But it's just a caution that, you have to be careful about how you treat eigenvalues, because you can technically have complex eigenvalues for real matrices. So that's just a little caution for you. Yeah, and so you might ask, like, what is this called? What is this polynomial here called? And the answer is that this polynomial is called the characteristic polynomial nomial of A. And so the roots of the characteristic polynomial of A give you the eigenvalues of your matrix A. So that's kind of all we're going to talk about eigenvalues. I've actually been misquoting. We're actually going to spend the next 3 weeks talking about basically the kind of math that underpins C-frames. So we're not going to go much more into eigenvalues, but eigenvalues are actually really cool. It turns out actually, you might think, oh, so you use, if you were like to code a method of solving for the roots of a polynomial, you could then use those to solve for the eigenvalues of a matrix. But it actually turns out it's easier to compute the eigenvalues of a matrix. And so you can do some clever math and find a matrix whose characteristic polynomial has the same roots as your polynomial, and then compute its eigenvalues, and that gives you the roots of the polynomial you're looking at. So there's a bunch of like crazy stuff you can do with eigenvalues like that. Compression algorithms are often based on eigenvalues. The first like green screen algorithms are based on eigenvalues and eigenvectors. There's a lot of cool stuff, but we're gonna kind of have to let eigenvalues kind of chill out for a while. They'll come back a little bit in the C-frame stuff. So yeah, that's going to be it for today. I'll turn off the recording.